Next, we're going to talk about the dot product. So the rule for the dot product, again, we're going to have two vectors. And what we're going to get when we take the dot product of two vectors is we're going to get a scalar. And how we're going to do that is I'm going to use an example in three-dimensional vectors. It doesn't need to be, but we'll do that example here. So what we're going to do is we're going to multiply the first element of each vector, and then we're going to multiply the second element of each vector, then we're going to multiply the third element of each vector, and we're going to add all those together. And that is going to be how we do the dot product. So for example, I'll do a couple examples. If we take, for example, 0, 1, 2, dotted with 3, 4, 5, that's going to be 0 plus, that's 0 times 3, plus 1 times 4, that's 4, plus 2 times 5, that's 10, so that's going to be 14. Let's get some examples with our standard basis. This will be a fun, we'll do a normal example and then a weird example. So let's say we did 3i plus 2j. Oh, I'll make this one just a little fun. And we dot that with 2i minus j plus k. That means that we're in three dimensionals. There's a secret 0 here. If we do that, we multiply the first component of each. That's going to be 6. 2 times 3 is 6. Plus the second component of each, that's going to be 2 times -1. That's -2. I should take a moment to say, when we multiply the first component of each, this is a good time to note that this I is not the square root of -1, so we did not get a negative sign out of that. It's just kind of telling us this is the first entry of this vector. So that got us 6. The second one was 2 times -1. And for the third one, well, there's a 0 here. There's a secret plus 0k here. And that's 0 times 1, which is just going to be 0. I don't know why I put parentheses, but we add that together and we're going to get 4. And now let's do a similar example. We're going to do the vector I dot the vector j. And to make sense of what this is saying, we probably want to write this out in some different notation. So this is going to be 1, 0, dot 0, 1. That's going to be 1 times 0 is our first term, plus 0 times 1 equals 0. And getting 0 is actually really important for us. The key fact, there's a few cool things about the dot product, but the key fact is that if A times B equals 0, the vectors are orthogonal. And what orthogonal means is there is a right angle between them. Kind of looks like I just crossed out the word. Pardon me there. And we can see that really clearly with the basis vectors. So if we look at the vector 1, 0, that vector goes like this. Actually, we'll use a different color. That vector goes like this. And if we look at the vector 0, 1, even though I did a really bad job drawing my coordinate axes, it looks like this. There is a nice right angle between those. This would even work if we were in 3 dimensions. So let's do an example, even though it's going to be kind of hard to draw. So let's look at the vectors. We'll do, How about 1, 2, 3? This should work. Dot. We'll do 0, -3, 2. Well, that's going to be 0 plus -6 plus 6, which will equal 0. So we're saying these vectors are orthogonal. Now let's see exactly how that works. So I'm going to need to draw a three-dimensional graph here. That's always fun. So we're going to have the vector 1, 2, 3. So our x-coordinate, this is our x-axis, our y-axis, our z-axis. 1, 2. I like to kind of do, well, we'll get back to that. 1, 2, 3. Whenever I'm drawing in several dimensions, I like to kind of draw myself some nice little grid lines to help myself see the 3 dimensions. So I'm going to actually draw a whole box thing here. That kind of helps the vectors seem to be in space as opposed to just a random dot pointing from the origin. So here is our vector 1, 2, 3. And then if we look at the vectors 0, -3, 2. So our x-coordinate 0, we're going to need to add a negative y-axis here. So that's just going to be here. Let's see here. That's actually pretty easy to draw. So that's going to just be -3, 2. If we draw that vector here, what it is saying is that there's actually a 90-degree angle between these. It's kind of hard to tell because they're at some weird angle, but if you rotated this picture around, kind of rotate it around, you'd get something that looks sort of like this. So the dot product being 0 tells us that these vectors are orthogonal, which is going to play a huge role in a lot of what we're going to study later this semester. So that's a really key fact I want to hammer in now.